Welcome you for joining our first lab online training class. There are going to be 4 training classes. It's based on the book I wrote in 2010. There are 12 units I will try to cover in this book. The first class will be very general. A few people already bought the books. If you didn't buy the book, that's okay. It's a book just for convenient for you. You want to keep it handy for your reference. Also, the materials covered in the PowerPoint presentation already. I will send it to you before the training. The objectives of this training provide you some basic knowledge for you to know. So after this training, you should have the following skills. You understand the operation principle of each instrument: GC, oxygen analyzer, moisture analyzer, BFTIR, THC analyzer. You understand the fundamental concept of statistical tools, such as percent RSD, standard deviation, regression, linearity. You have the ability to determine if a GC or other analytical method is acceptable. You will be able to understand the source of errors in measurements, provide a value without the uncertainty. It didn't really make too much sense for our analytical chemist. You should gain some basic troubleshooting skills for your common GC issues. And last, you have the ability to convert the units. Volume percent, volume ppm, or by mole weight is all different. You should be able to apply the ideal gas law. I mentioned that we don't talk too much about the equation because I try to make it simple, but it's one of the most important equations you should know. Pre-class reading, please read the book. The book is constructed this way. First, it gives you the test your knowledge question. Next section will be the contents of the unit. I'll tell you more about what kind of knowledge in this unit you should know. The last one give you a few questions, so you can do the self-assessment. You really understand after you read the contents of this unit. Test your knowledge. Question 1. Which of the following gases has the highest concentration in the Earth's atmosphere?
Nitrogen.
Yeah, oh, thank you. The study highlights of this unit is the composition of the atmosphere and the properties of some atmospheric gases we're dealing with, mainly for the pure products, for the UHP products. The gases surrounding the Earth is retained by the gravity. So without the Earth's gravity, it becomes the outer space, no air. The gases contains roughly about 78% of the nitrogen, 21% of oxygen, 0.9% of the argon, and about 300 ppm of CO2. The concentration of the CO2 has gradually changed from the last few decades. Now it's supposed to about 400 ppm. Kind of a concern for us, so something that we should know as well. Also, it contains other trace amounts of gases. We call it air. The atmospheres protect the life on Earth by absorbing the UV radiation and reducing the temperature extremes between the day and night. So it won't be too hot and too cold. Roughly about 3/4 of the atmospheric gases are within 11 kilometers from the Earth's surface. This table is literature that listed in 1990s. The nitrogen have 78%, oxygen about 20.9%, and argon 0.9%. You see the CO2 at that time is roughly about 300 ppm. And you contain the other trace components: neon, methane, helium, hydrogen, etc. Let's take a look at this chart. It's very interesting. This is called the Killing curve. This researcher in Hawaii, he monitored the concentration level in one of the Hawaii islands from 1958, starting from about 300 ppm. Now it's over 400 ppm. So you can see the CO2 concentration gradually increased since 1960. It doesn't matter if people believe global warming or not, but the fact is the concentration of CO2 increased. So you can also see this is very interesting. Even different seasons, there's a variation in the CO2 concentration. In Hawaii, in April, it has the highest CO2 concentration. In October, it has the lowest concentration. plus or minus roughly about 2 ppm. So depending on the area you are in, the CO2 concentration that you monitor could be different. What's the difference between the compressed air and the blended air? Compressed air directly compressed from the atmosphere air to the cylinder or to the container. So it contains those impurities. Unless you purify it through the emulsive column to remove the CO2 and moisture. Compress the air directly to the cylinder. So you still have roughly 300 400 ppm of CO2 in the cylinder. Blended air, the people use the raw material of oxygen and nitrogen. Okay, roughly the ratio will be, like 79% nitrogen and 21% of oxygen. They use those two materials to compress into the cylinder. It will not have that much impurity. All the trace impurity will be from the raw material, the UHP nitrogen or UHP oxygen. Very low ppm impurity. So that's the difference of the compressed air and the blended air, just for your information. We want to know some of the atmospheric properties you handle in the UHP products. First one is the nitrogen. It's colorless, non-toxic inert gas, but it's not a life-supporting gas. It's not flammable, it won't burn, it does not support the combustion. It's slightly soluble in water. It's a poor conductor of electricity and heat. It's commercially used in heat treating of primary metals, production of semiconductor part components. It's used as a brine of foam type of plastics, in degassing of non-ferrous metals, used in the food processing and packaging. Also, it's an inhibition of aerobic bacterial growth. The liquid nitrogen is freezing the perishable foods. It can be used to cooling of concrete. Can be used for preservation of whole blood and other biological substances. And can use to remove the blemishes in the dermatology and use a coolant for the electronic equipment. Oxygen is an oxidizer. It's a colorless, tasteless, but it supports the life and combustion. So it supports life. If the oxygen below the certain concentration level, it produces a life-threatening situation. So as we see in previous table, oxygen roughly is about 21%. You should have a life safety system in your laboratory to monitor the oxygen level if you're dealing with the bulk analysis. Okay, OSHA, that's just for your information. They define the range 19.5 to 23.5% of oxygen is best suitable for human. I don't know what your oxygen deficiency monitor set it at, but it's below 19.5%, it should give you the warning. All elements except the inert gases react with oxygen to form the oxide. Some inert gas at high temperature, oxygen, right, with nitrogen. So at high temperature, with lightning, can form some kind of oxides in the atmosphere. Phosphorus, it will ignite spontaneously in air, even at ambient temperature, because of the oxygen. Normal metals oxidize only at very high temperature. Normal metals like platinum. Oxygen is non-flammable, so readily supports combustion. When we learn about the triangle thing, oxidizer fuel, you have an ignition source. For the location handle, both oxidizer and flammable need to be extra careful. Oxygen is commonly used in the medical application. So some location provide medical oxygen, high altitude flying, used in the deep sea diving. It's the power source in the U.S. space program. Metal cutting, welding, hardening, and scarfing. Argon is a rare gases, along with the helium, neon, krypton, and xenon. So it's a very inert. It's colorless, tasteless, and non-toxic, but it's slightly soluble in water. It's extremely inert and forms no known chemical compounds. The periodic table, you have the atomic number, 18 of argon. Also, you give it the atomic weight. Use basic information, you calculate the molecular weight of molecule. So argon is commonly used in the inert gas, shielding gas, the welding, fueling the fluorescence lamps, and electronic tubes. It can be used as a blanket gas in the production of titanium, zirconium, and other reactive metals. It's a protective atmosphere for growing silicon and germanium crystals, and also used in the museum to protect the materials. Carbon dioxide is relatively non-reactive and non-toxic. It does not burn, it does not support the combustion of life. But when dissolved in water, carbonic acid is formed. So all the soda we use, Coke or Sprite, for the CO2, you know that it's acidic because of carbonic acids. Carbon dioxide may exist simultaneously as a solid, liquid, and gas at a temperature of minus 69.9 degree F and a pressure of the 60.4 psig. You have a solid, liquid, and gas phase coexist. This is called the triple point. It's a very interesting just for the CO2. It's called a greenhouse gas. CO2 transmits a visible light by absorbing strongly in the infrared. You have an infrared sensor, it can sense the heat. So a lot of temperature sensors use the infrared. So CO2 is commonly used to produce carbonated soft drinks and soda water, refrigerate dairy products, protect the meat products, be a growth stimulant for plant life. You can test aviation, missile, and electronic components. Simulated oil and gas well, and fuel the fire extinguisher. We use the CO2. Helium is a family of rare gases. As we know, it's inert, colorless, tasteless, non-toxic. It's the second lightest gas. Which one is lightest gas? Hydrogen, right? Although helium is a non-toxic gas, it can replace the oxygen by diluting the concentration of oxygen. So if you analyze whatever other bulk gases laboratory, you should have a life monitoring system, the oxygen deficiency monitor. Helium is commonly used in the fueling the balloon. Although the hydrogen is lighter than the helium, we don't use the hydrogen because it's a safety hazard. You can use a carrier gas for laboratory gas, GC, the nuclear reactors as a coolant, the arc welding processes on materials, on shielding gas, fueling the cold weather fluorescence lamps used in the superconductivity research. Hydrogen is a highly flammable gas. It's colorless, odorless, non-toxic. It's the lightest gas known with a concentration of about 0.5 ppm by volume. The flammable limit of the hydrogen in air is between 4% to 75%. That means below 4% it's non-flammable, above 75% is fuel in rich environment, so it won't burn. Between 4% to 75% in air, it causes an explosive mixture. LEL is called a low explosion limit. In this case, hydrogen is 4%. UEL is the upper explosion limit. In this case, 75% is for the hydrogen. Hydrogen is commonly used in the production of methanol, increasing the level of saturation, unsaturated fat, and oils. Reducing metallic ores as a reducing agent or used as a fuel for the laboratory instrument. For example, your FID, flame ionization detector, use hydrogen, or your TSC analyzer. Some use a pure hydrogen, some use a fit fuel. Now, it can be used as carrier gas. It's not popular, but you can use it because it provides shorter runtime, faster analysis. For some safety concern, we're going to talk about it in the next few slides. We try to minimize the use of the hydrogen as a GC carrier gas. It can also be used for production ammonia. Hydrogen hazard is an important topic that we need to talk about in the laboratory. So high-level summary for the safety. Hydrogen is colorless, odorless, tasteless. It's flammable when mixed even small amount with ordinary air. So hydrogen gas and normal air can ignite as low as 4%, which is known as LEL. Due to the oxygen in the air and the simplicity and the chemical property of the reaction. And the storage and the use of hydrogen possesses a unique challenge due to its easy of leaking as a gas still. Sometimes it's hard to trace it for the minor leaks. You need to pay extra attention to all the leaks when you do the hydrogen. So you never let it run overnight unattended. It will generate the impurity for the hydrogen. It also has a buoyancy effect and its ability to embrittle the metals. The flammable limit is between 4 to 75%. If it's not in air, it's existing in oxygen. UEL increased to 94%, even give you a more wider range. So when you check the LEL, UEL, you need to know the matrix. Sometimes it tells you it's air, sometimes it tells you it's in the oxygen. So the table is different. Okay, the limits of detonability of the hydrogen in air is 18.3 to 59% by volume. So detonation is an extremely violent explosion. It's like produce the explosion through the heat transfer in the speed over the sounds, like a supersonics, the shock wave. So it's produce a more violent explosion. The flame in and around the collection of pipes or structure that can create turbulence, that cause especially as a cylinder as well. So we talk about the pipes, you talk about the cylinders. They all look like the tubes, the pipes. It causes deflagration to involve into the detonation. That's why we say if you have a cylinders only in use, hydrogen, you put in the laboratory. If it's not in use, you don't put it in the laboratory. Don't just say, I want to save time, try to put all the hydrogen in the laboratory. If it's not in use, you don't put it in the laboratory. So for comparison, the deflagration limit of gasoline is 1.4 to 7.6%. But acetylene is much wider, it's much dangerous range. You need to know what chemicals you're dealing with. You need to read the MSDS. We work with flammable materials. You can separate oxygen, other oxidizer by rules. Hydrogen is odorless, colorless, it tasteless, right? So most human sense just won't help you to detect the hydrogen leaks. By the comparison, our natural gas also is odorless, colorless, tasteless. As an industrial, always add some kind of sulfur-containing odorant, mercaptans. When you have leaks, you can smell it at home. But the hydrogen, really, we don't add anything, no sulfur components, mercaptan. So you can use your nose to smell it. Given the hydrogen tendency to rise quickly, the hydrogen leaks indoors will briefly collect on the ceiling because of a buoyancy effect. It could collect in the corners or away from any nose might detect it. Nose won't detect it anyway. So hydrogen leaks can lead to a combustion at very low flow rate, as low as 4 micrograms per second. It's roughly under the cc per minute. That could give you the trouble if you accumulate it over time. For your information, some hydrogen can embrittle the metal, even the stainless steel. If you use a stainless steel tubing, you need to inspect it regularly. Also, the hydrogen embrittle a variety of substances, because stainless steel, aluminum, titanium. Just for your information, no issue with the copper tubing. In all the laboratories, they use copper tubing too. But copper tubing, this concern is like it put too much tension. You bend it, it could break easier compared to the stainless tubing. Handling of the hydrogen cylinders. Cylinders should be handled only by trained personnel. You got a new employee, you got new chemist, lab techs. You need to put them in the training how to handle the cylinder. Cylinders that are not necessary for current laboratory requirement should be stored at a safe location. If that's not in use, you cannot put 10 hydrogen cylinders just for your convenience in the laboratory. Cylinders should be secure from tipping over. A cylinder in the laboratory should be equipped with a pressure regulator that's designed for the hydrogen. So hydrogen, you have a CGL 350. You use a right regulator with the right CGL. You cannot just open the hydrogen cylinder without the pressure reducing device. Like in this case, will be cylinder regulator. Regulator should be equipped with 2 gauges. So you should be able to read the input pressure 2000 psi or 2400 psi. You have output pressure rating. It's 100 psi, 50 psi. Just remember, some of your detectors, FID, they have pressure limit for your instrument. If you don't have gauge or you select the wrong regulator, it could damage your system, damage your detectors, damage your inlet system. Especially for the newer GC, as 870 and 90s, user have a programmable pressure control, electronic control, it could damage it. Just make sure that you have 2 gauges when you use a hydrogen cylinder. Where the source cylinder is outside the lab, a station regulator and gauge should be installed at or near the point of view shows the outlet pressure. Put the fuel gas hydrogen outside the laboratory, that's fine. Inside, before the instrument, you should have a regulator to monitor what's the pressure of the hydrogen. Hydrogen supply lines should have a manual shut-off valve to allow the isolation of the equipment. Just in case you found some leak in the system, you should be able to shut off the hydrogen supply. The cylinder should be attached to an instrument or used by means of a regulator. You need to really look into your safety, evaluate your safety situation. Ask your regional lab manager, your operation manager, because it's not safe if you don't have a regulator. You try to operate the hydrogen. What's an in-use hydrogen cylinder? A compressed gas cylinder should be considered in use in the following condition. It's connected through a regulator to deliver hydrogen gas to a laboratory operation. Or it's connected to a manifold being used to deliver hydrogen gas to a laboratory operation. Or it's a single cylinder secured alongside with the primary cylinder as a reserve cylinder. That should be okay if you have a changeover system. When one is empty, the other one automatically kick in to supply the hydrogen. Cylinder is not in use, should not be stored in the laboratory. That's very important. Hydrogen cylinder located outdoors should not be installed within 10 feet of the windows when not in use, okay, or other built-in opening, or within 50 feet of ventilation intakes. The storage area should have a minimum of 25% of perimeter open to the atmosphere. It's just a general guideline. This open space can incorporate chain link fence, that is construction, open block, or similar materials. Okay, storage area should be kept clear of dry vegetation and combustible material. Like any materials, could be your wooden pellets or something. At least 15 feet. Cylinder stored outside should not be placed on the ground or the surface when water can accumulate, so it can rust your cylinder. Let's talk about a case study for the lab incident. It's published in June 2010. It's a real story. An explosion injured 4 people at the University of Missouri Science Lab Monday afternoon was caused by the human error. Lab personnel failed to turn off a hydrogen tank during an experiment, and the building concentration of gas eventually exploded. So the glass and debris from the third floor biochemistry lab had ruined down onto the sidewalk, courtyard, and driveway to the building. Injured people were transported to the hospital. Hydrogen hazard is critical. We need to pay attention to it. Even the university seems like their chemistry background, they know about the chemistry. They understand the hazard, but you don't pay attention, it could cause an accident. Safety tips you can use in your safety training as well. Safety tips for incident prevention for the hydrogen hazards. No open flame or smoking in the area when hydrogen is in use. Work in the area of plenty ventilation. If you work in the confined space, you need to figure out you have good ventilation. If there is hydrogen, you don't vent the hydrogen directly in your laboratory. You should have a vent line. If not, then you need to ask your supervisor, your branch manager. Do not run the hydrogen sample cylinder overnight. That's very important. You run hydrogen, maybe you have 10 samples today, you cannot finish in your shift, but do not run overnight. That's very important. That's a policy. You need to shut it up. And ground all the equipment and piping used with the hydrogen. And make sure that you are properly grounded. So you know how you ground it? You touch a piece of metal, you make sure you ground it. Because if you don't ground it, especially for some dry area. Sometimes you get the static electricity, like that's an ignition source. It's very important. So rubber sole shoes prevent you from being grounded. So you should touch a grounded object to discharge you up static electricity before beginning the work. So if you work for the analysis of the hydrogen, that's a knowledge that you should have. Wear appropriate lab safety gear for the work being performed. Safety glasses, goggles, lab coat, gloves. We don't use a face shield. But in the laboratory, if you do the research lab, you perform some synthesis reaction, then you need to consider that in case there's an explosion. Working with the liquid hydrogen, I don't know anybody in this class working with the liquid hydrogen, but you must have appropriate insulated gloves and protective shoes in addition to the appropriate safety gear. Remove unnecessary electrical equipment or electronic devices from the vicinity of the hydrogen gas. Okay. You don't need it, don't use it, like a heat gun or something, so need to be handled very carefully. Use metal piping with hydrogen. Do not use non-conductive or plastic tubing. Okay. Make sure you vent. Do not use a plastic if you handle with hydrogen. Okay. Hydrogen cylinder must be stored with a valve protective cap in use. Not only the hydrogen cylinder, all the cylinder, including the flammable, non-flammable, if it's not in use, should be kept. Hydrogen cylinder must be stored more than 20 feet away from the cylinder oxygen and other oxidizer. Never open the cylinder valve before making sure your connections are secure. This is very important. So even you connect a regulator, make sure all the connections are tight. Sometimes you, in a rush, you forget about it. Without checking it, you thought it's tight. Or when you connect your cylinder, somebody talk to you, you forgot to tighten it, use the wrench. So make sure double check when you handle the hydrogen, it's very important. If you open it with the connections loose, it could create a very dangerous situation. Because with a static discharge, you throw in the gas through the leaking area that could cause the hydrogen to be ignited. You should never use an adapter for the hydrogen. Hydrogen uses CGA 350. Anytime you use an adapter, you should lock it. Per work instruction, you should lock the use adapter. Be aware of the leaks. Hydrogen has a low viscosity. It could make it to very high leakage rate. Due to the hydrogen low molecular weight, the gas will diffuse rapidly in a room and collect it near the ceiling. All electronic equipment used near the hydrogen gas must be grounded. And check that the pressurized system does not leak the hydrogen with a leak detection solution or a leak detector before actually run the samples. And close the cylinder valve when not in use. Do not leave the piping or pressurize if not in use. So that means when you finish it, at the end of the day, you should vent it to the vent line. Okay, don't let the pressure build up in your tubing. Hydrogen is incompatible with many materials and situations. It ignites easily with oxygen. It reacts violently or explosively or forms a heat and shock-sensitive explosion mixture with oxygen. A mixture with chlorine may explode on exposure to light. Mixture with oxygen may explode in the presence of platinum catalyst. They found a hydride. If you work with hydride, when heated with alkalis or alkaline earth and some other elements. The general question, then a few gas use carrier gas or UGC. Which carrier gas is flammable? Anybody? Good. All right, this question in the book, I don't think I want to go through this, just save time, but it's in the book, but also in this PowerPoint, you can practice it. At the very end of the book, it gives you the key to each question. You can check how good you have to complete the training. Unit 2, so let's test your general knowledge. Gas vendor supply you a UHP helium with a 99.999. What was the allowable concentration for the total impurity?
10 ppm.
Good, thank you. It's very straightforward. We talk about the purity And typical impurities in the pure products, mainly we deal with like hydrogen, nitrogen, some other location doing the hydrocarbons, freon, but that's okay. The same concept can be applied. This is just a cheat sheet for you if you're new to this industrial. So purity for the 99.9999%. It's a maximum impurity of 1 ppm or 0.0001%. You follow this table, if you have 99% purity, that means you have 1% impurity or 10,000 ppm. What's a ppm? ppm is called a parts per million. It's a term to use frequently in chemistry to express the concentration of a substance in trace label. ppm is a pure number. It's a number with no associated unit of measurement since it's a ratio of quantity per quantity. So you tell me it's 10 ppm. You don't give me the unit. It's 10 ppm by mole, by volume, by weight. You didn't tell me the complete information. So it's a ppm is a pure number. Okay, for example, the expression of 1 ppm oxygen in helium, it simply means 1 part of oxygen existed in 1 million parts of helium. The part could be volume, could be weight. So you tell me 1 ppm oxygen in helium, what does that mean? 1 ppm volume, 1 ppm weight, mole, those things. This tells you the relative abundance of the oxygen in this example in the helium sample. Question. An analyst requests a gas standard. Want to order 100 ppm methane balanced nitrogen. Something missing in this request? Of course, it could be what kind of cylinder, what's the pressure you want to fill, those things. But I probably have standard part number for it. The most important is you didn't give the unit. You give 100 ppm. It's by mole, by weight. Normally, our standard, we order it by mole. Sometimes we assume by mole, but sometimes the customer want to order by weight also. So you need to know. In addition to ppm, there's a ppb, ppt. There's even trace label. In some of your electronic spec, you have a ppb spec, moisture. Metal analysis sometimes maybe has ppt specs. So definition is similar. ppb is a 1 part per million. PPT is 1 part per trillion parts. It has a concentration of 10 to minus 12. This is just a spec, a copy from catalog. At the time of 2010, maybe it could change by now. Maybe you got a different spec, but that's just information. Now, let's look at it. For helium, 99.999%, you got oxygen spec less than 2 ppm. Moisture spec less than 2 ppm, THC less than 0.5 ppm. But you have individual concentration for the impurity. However, total impurity need to be less than 10 ppm, as we talk about. So you got an individual spec, you get a total impurity spec. Based on this, let's do a quick test. Just pick one. Test 4. Your lab analysis indicates the impurity in argon cylinder are as follows. Oxygen 1.5 ppm, moisture 0.9, THC 0.4, CO 0.2, CO2 0.1 ppm. Does this cylinder meet the UHP argon specification? Yes or no?
CO2 fail.
Good. Yeah, CO2 fail. Good. Thank you. So CO2 spec is 1 ppm. CO is 1 ppm. So your CO2 fail. When you check your spec sheet, so you perform the analysis, check the total impurity, check the individual impurity, make sure it makes a spec. So that's pretty straightforward. The unit 3, test your knowledge. Question 3, a nitrogen cylinder has a pressure of 2000 psi at 32 degree F. What is its pressure at 80 degree F? Roughly about 27 degrees C. Assuming the nitrogen is an ideal gas, we choose the closest answer. Should it be higher or lower than 2000 psi? At higher temperature, should the pressure be higher or lower?
Higher.
Okay, good. Thank you. Then we will look at how to calculate this. What is an ideal gas? So there's some assumptions. When the scientists derive this ideal gas law, ideal gas is hypothetically assumed that it will exhibit following 4 properties. The first one is molecules do not occupy the volume, so it's small. The smaller molecules should exhibit more ideal gas behavior in this assumption. Big molecule won't be the ideal gas. The second one, the molecules are in the constant random motion. Don't limit it to just move one direction. It's randomly moving. Number 3, there are not any intermolecular forces between the molecules. So molecules don't interact with each other by the force. And the collision involved the gas molecule are totally elastic. That means those two molecules collide with each other, they lose no energy. These are the 4 assumptions. So people use that to derive the ideal gas law. There are not many equations we need to remember. This is one of the equations you should remember. So real gases do not behave according to this property, but they will behave more like an ideal gas at either high temperatures or low pressure. For example, at higher temperature, the gas molecule have a much higher energy. So intermolecular force become negligible because you have more energy for individual molecule. So at the lower pressures, the chance for gas molecule to collide is significantly lower because it's far apart. So the real gas at the high temperature or low pressure, they behave not more like an ideal gas. The ideal gas law expresses the relationship of the pressure, temperature, volume of an ideal gas. So many common gases exhibit the behavior very close to ideal gas at the ambient temperature and pressure. So the ideal gas was originally derived from the experimentally measure of the Charles law and Boyle's law. Charles law talking about constant pressure, the volume is proportional to temperature. Boyle's law, the constant temperature. Pressure is inversely proportional to the volume. The scientists derived ideal gas law. PV is equal to nRT. That's one of the most important formula you need to remember. P is the pressure of the gas. The unit where we use the atmosphere, ATM. Volume has a unit in liter. N is moles of a gas. R is the gas constant. With all the unit that we use here is 0.082 roughly. T is the temperature of the gas. The temperature unit is absolute, expressed in the Kelvin. Celsius to Kelvin. Celsius plus 273 equivalent to absolute temperature. You know how to convert from Fahrenheit to Celsius. For example, 27 degrees C is 27 plus 273 K, about 300 K. To solve that question, you got 2 different temperatures. Ratio will change too. So we know the ratio because of PV nRT. So P1 versus P2, the pressure 1 versus pressure 2 should be equal to temperature 1 a ratio to temperature 2. At higher temperature, you should get a higher pressure. P1 is the pressure at the temperature 1. T1 is a temperature 1. T2 is the pressure at the temperature 2. T2 is the temperature 2. So at lower temperature, you will have a lower pressure. So that's why in the winter time, so like a CO2 mix 2000 psi originally, now it dropped to 1800 psi for that reason. Lower temperature, low pressure for the same volume. Back to that question. So the pressure 1, originally we got 2000 psi. Remember, we need to convert to PSIA. PSIG is the pressure at gauge. That means you put a regulator, if you did 2000 psi, that's giving you the pressure at gauge reading. At high pressure, 2000 psi, 2000 plus roughly about 15, you get a 2015 psia. Make not too much difference from 2000 to 2015. Why do you care about this 15? But for the low pressure mixture, that make a lot of difference. For example, you make the hydrocarbon mixtures due to condensation issue. Sometimes you calculate at lower pressure. So sometimes you get 10, 20 components contain the heavier components. Pressure could be only 20 psig. So that really is a 35 psia. Okay, you add 15 to it. 35 versus 20, that's a significant difference. That's why we converted here 2015 PSIA to give you the correct calculation. T1 at 0 degrees C is 273 K. P2 at temperature 300 degrees. What would be the pressure? Based on this equation, it would be P1 times the T2 divided by T1. So that's roughly about 2214 PSIA minus 15, so we got a 2199 PSIG. That's what you should read at the gauge on your regulator. It will assume that's ideal gas, which is very close. I give you some notes here. PSIG is a pound force per square inches gauge. This is a gauge reading. It's a unit of pressure relative to the surrounding atmosphere. I mean that we put a gauge in the atmosphere, it reads 0. But is this really 0 pressure? No, we already have 1 atmosphere. When we stand in the ground, we already have 1 atmosphere. So 1 atmosphere pressure is there. So we reading gauge 0 doesn't mean the pressure is 0. When you put a vacuum from the cylinder, it's close to 0 pressure in the cylinder when you put a vacuum. So you start to fill the gas into the cylinder, or you suck the air from the atmosphere when you open the valve. Eventually, it's going to equalize it. At that time, you equalize it, you put a gauge to measure it. The gauge is still 0, but it's not really 0 PSI. It still has 1 atmosphere. So we call the PSIA is a pound force per square inch absolute. So 1 atmosphere roughly about 14.696 PSIA. So that's a conversion here. 2000 PSIG is 2015 PSIA. Let's talk about the compressibility factor. So we know the ideal gas PV is equal to nRT. But for some real gas, it doesn't behave the real gas behavior. There is another term you put into the equation. It's called the compressibility factor, Z factor. It's a correction factor which describes the deviation of the real gas from the ideal gas. Normally, the Z factor is less than 1, it could be higher than 1 for helium, hydrogen. For most of gas like CO2, it could be less than 1. Sometimes you try to fill based on your ideal gas calculation. You calculate 1600 psi or lower, depends on the composition of the CO2. So the ratio of the mole volume of a gas to the mole volume of the ideal gas at the same temperature and the pressure. It is a useful thermodynamic property for modifying the ideal gas law to account for the real gas behavior. Some locations don't handle hydrocarbons or material like CO2, you won't have issue. But some you do, then you need to consider compressibility factor. So which of the following gases behave more like a real gas compared to other at 2000 psi? Nitrogen, argon, helium, hydrogen, carbon dioxide. The CO2, right? CO2 is the molecules are bigger and the boiling point higher compared to other molecules, and it's more compressible.